Hello, and welcome back to a video series on MAC 1140 Precalculus Algebra. My name is Sean Perry. This is guided notes number 8 in the series on section 2.3, exponential functions. The first question asks for us to pick out what family this equation belongs to. Let's actually do a little bit better and define what each one of these families means. An exponential function is one that can be written in the following way. We have a constant, perhaps, times a number, another constant, raised to the power of x. And for this section, we are going to first of all require that b is positive, and second of all require that b is not equal to 1. So we won't be dealing with any negative bases, because then raising them to some fractional power might give me a complex number. And we're not going to be dealing with 1, because if we just have 1 raised to some power, I get 1 back, and this would just be a flat line at c. Logarithmic functions will be similar, where I could perhaps have a constant times a logarithm, base b, and we'll learn how this is actually the inverse function, or related to the inverse function of the exponential with base b. The same constraints on b will apply. For quadratic functions, we've actually seen quite a bit on those. In the same sense, we've seen a lot about linear functions as well. So now looking at the function they gave us, this is clearly a y equals mx plus b type equation. This thing is linear. If I go to plug in a few values here so we can plot, we'll have the line pass through 0, 80, and with a slope of minus 60, it'll go down by 60 every single time I go up by 1. Likewise, if I go back by 1, this is going to go up 60, the following values. If I'm going to plot these, I'm going to need a particularly big graph, good enough, although our points are actually pretty well tucked in between these points here. Well, let's give it as a good a go as we can. 0, 80 is here. If I cut this into 5 relatively evenly sliced pieces, going over by 1, it's going to go down by 60. And to be perfectly honest, I think these are the only 2 points we're going to be able to fit on this graph. Sure, let's connect them. And without getting too bent out of shape about how narrow this window really was, let's move on. So here we have something which is clearly a exponential. This is b raised to some power of x, where b is equal to 1/6. Which does follow our criteria of being greater than 0 and not equal to 1. If I plug some values in here, anything to the 0th power is 1, anything to the first power is itself, and squaring this, we would get 1 over 36. Now, if I take the negative first power of that, it would be the reciprocal of 1/6, which is 6, and the reciprocal squared would be 36. Let's see how well I can plot these points. We have 0, 1, we have 1/6, we have negative 1/6, we have 1 1/6, we have 2 1/36. Let's try to connect these points as best we can. We have this particularly sharp bend in the curve, and then we'll actually just get smaller and smaller values, so there's this kind of horizontal asymptote off to the right, and this incredibly steepening function off to the left. I think that's as good as we can do with that one. So here we're asked to consider this function f of x is equal to e to the minus x plus 9. We'll learn more a little bit about e later on, how it can be defined in terms of a limit. As n becomes larger and larger, this gets closer and closer to e. But for right now, I want you just to think about it in terms of an approximate value. The same way that when you first learn about pi, it's okay to think of it as 3.14, even though we know it goes on forever without repeating as a decimal. E is very similar. It's an irrational number whose decimal never develops a repeating pattern, and I'll just say that it's a very fundamental math constant for right now. But that being said, it is a positive number, larger than 1, and as such, we do know some values that it will go through. We know that when I raise something to the 0th power, it winds up going through 1. And likewise, if I raise something to the first power, it goes through itself. And as such, this is going to be some number between 2 and 3. Just by connecting these 2 points, we can sort of see where the tail of this exponential function will lie. It's going to be off to the right. And as you might imagine, if I get larger and larger powers of e, well, the larger the power of e, it will get very large indeed. But that means that e to the negative n, which is 1 over e to the n, will get very small indeed. So this is the behavior that we see. As we go in the negatives, because e is a number greater than 1, 1 over that, or e to the negative power, is going to get to be a very small positive number. So the asymptotic equation here is going to be y equals 0. The range, well, it's going to swoop up towards infinity here. It's going to keep on rising, but it's never going to get lower than 0. it's never going to be equal to 0. So the range is going to be from 0 up to infinity. Similarly, we could approach this one with 2. 2's pretty close to e, but we're going to want to also pay attention to these function transformations which have been applied to the exponential function 2 to the x, right? 2 to the x would look almost exactly like e did, with a tail going one way, rising through 0, 1, and going through 1, 2 this time, and then increasing. But so what would it do if I subtracted 2 on the inside and added 5 on the outside? Well, let me draw a slightly smaller version here so that we can fit all the pertinent details on the map. So there's 2 to the x again. Now, this has been increased by 5 points for every y value. So instead of having a horizontal axis, instead of having the x-axis as my horizontal asymptote will have been moved up 1, 2, 3, 4, 5 points as such. And this minus 2 here means that we are going to arrive at x values 2 later. I will be at 0 for my entire argument when x is positive 2. So this has been right shifted by 2 units for each and every point here. So for example, the point that went through 0, 1 now goes through 2, 1. Plugging in 2, I would get 2 to the 0. And also has been upshifted by 5 units. So we're now going to go through 2, 6. Likewise, this point of 1, 2 has been shifted over by 2 units at 3 and up by 5 units at 7. And so these 2 points will be on our graph. This is actually enough to plot our function, just like this, and we would get a graph of 2 to the x minus 2 plus 5. From the graph, we can see the range and the domain and all of these other equations. The equation of the asymptote has been upshifted to y equals 5 instead of the previous y equals 0 that it was before. The domain is still negative infinity to positive infinity. All exponential functions have this domain because I'm allowed to raise 2 to whatever power I like. It might get humongous, but I'm still allowed to raise 2 to that power. But now the range has been shifted. It's no longer from 0 to infinity. It's been upshifted by 5 units. So 0 is shifted up to 5, but infinity stays at infinity. Here we're asked to complete this table. Notice that we are composing a negative sign into the x, which is the same as horizontal reflection. We should notice that 7 to the minus x is the same thing as 7 to the minus 1 to the x. In other words, this is the same thing as 1/7 to the x. So the behavior of having an asymptote on the right-hand side that we observed for 1/6 is going to follow along, and that's going to look exactly like a horizontal reflection. So let's plot a few points here. If I plug in minus 2, we get a square of 7, which is 49. Here I would get 7. Here I would get 1. 1 plugged in here would be 1/7 because we'd have a negative 1 power, and this would be 1/49. Plotting a few of these points as best we can, we have 1, 7, I can fit on the map. 0, 1, I can fit on the map. I can approximate 1/7, and 1/49 I'll give just a hint about, right? We connect these points, and we see some of the main features of the graph. The horizontal asymptote going off to the right, the exponential growth when we go to the left, although when we have a graph like this, we refer to this as exponential decay. In the same way we think about slope with x's going to the right, as we go to the right, this thing becomes arbitrarily close to 0, and so we call that exponential decay. The reverse situation, where things get arbitrarily large as you go to the right, we call exponential growth. Here we're asked to use a table to graph this fractional base. It's going to have a similar look to the one that just came before because it's going to be exponential decay. We can tell that something is exponential decay just by looking at the base. If it's less than 1, that is to say between 0 and 1, it's going to be exponential decay. What do I get when I raise something to the first power? I get itself. We just get the base here. The square of the top and bottom would be 4/25. The 0th power of anything will be 1. Other than 0, I should point out that 0 to the 0 is very much undefined. If we go minus 1 on this, we're going to take its reciprocal, that's 5/2, and the square of that will be 25/4, or 6 1/4. So let's try to graph some of these things. We go through 0, 1. We go through 1 2/5, which is 4/10, something about here. At 2, we're at 4/25, which is a little bit less than a fifth, so something down here. At minus 1, we're at 5 halves. That's 2.5. That's a nice clean point there. And I don't think we can get up to 6.25, which would be off here. So let's just imply it. Connect these dots, draw this asymptote, and that's a good enough sketch of this graph. This is decay. As we go towards the right, if it starts hugging this asymptote going towards the right, this is exponential decay. Here we're asked to remember some transformations. How do we shift 3 to the x upward? We add 3 to the outside. How do I shift something to the right? I compose this by minusing 2 from it, because this is going to cause me to be, for example, where this one would have had argument 0, we'll now have to be at 2 before it has argument 0. So minusing 2 means we'll get to these values of the argument or the exponent 2 units later. Now, how do we reflect around the x-axis? This is going to be multiplying on the inside by a negative. If we wanted to reflect around the y-axis, we would put that negative sign on the outside, and if we wanted to do both, well, then we would do both. So we would continue to review the transformation rules. Here we have left shifted by 4 and down shifted by 7. That's going to be this one. Let's take our time with this one because there are 1, 2, 3 transformations which have been applied. First of all, let's consider, for example, what would it be if I graphed minus 4 to the x? Well, this would be a vertical reflection of the graph 4 to the x, which would pass through 1 and also through 1, 4. Okay. If I then took this graph and transformed it by adding 2, this is a leftward shift by 2, which would take these 2 points and shift them left by 2 units. And likewise, if I took a look at the full function here, minus 4 to the x plus 2, and now I upshift it by 3, that takes these points and brings them up by 3. 1, 2, 3, and 1, 2, 3. Notice it was only that upshift that really changed the location of my horizontal asymptote. Neither the reflection of 4 to the x over the axis nor its horizontal translation changed my asymptote, but if I increased everything by 3, that also increases the asymptote. I don't think this is in quite the right place. It should be increased by 3 units, right? So that should bring it up to, there we are. Now we have an asymptote at y equals 3. So let's graph everything that has to do with that, right? But I meant to show you all these because you can think about these transformations one at a time. You need not think about them all at once. But it's our vertical translation, which is going to do so much to change our horizontal asymptote. What would have gone through the point 0, 1 has been flipped, right shifted, and upshifted to be here. What would have gone through the point 1, 4 has been flipped, left shifted, and upshifted to now go through -1, -1. And if we complete this drawing, we get the following curve. Here we're asked for something similar. I'll proceed without drawing all of the extra frills, right? But I will say that we should probably at least understand what's going on with the original parent function 4 to the x. That's going to look like something which goes through 0, 1, 1, 4, and has a horizontal asymptote which decays off to the left and has exponential growth on the right. So now what about this function? Well, this function is nearly the same as 4 to the x. It's simply been right shifted by 3 and upshifted by 3. So we want to take our 2 points that we know a lot about. We want to shift them over and up. We want to take this asymptote. We want to shift it up. We don't need to shift it over because that wouldn't change anything about a line of horizontal nature. Shifting this over and up, here is my new asymptote, and here is where my points are going to go. Over 3, up 3, over 3, up 3. And so I have something which hugs the asymptote on this side and then lifts up to grow and connect these 2 points. And that would just about do it for this graph. Question 11 asks us to evaluate this expression or series of expressions. We can see a pattern here. We have small decimals being added to the number 1 raised to successively larger powers of 10. And we could do this quickly by plugging this in as a list into the calculator. We have to first decode the pattern. Here I've written it as 1 plus some small fraction power of 10, so 1 over 10 to a power here, to the power of 10 to some power. So for example, 1 plus 100th to the power of 100, or 1 plus 1,000th to the power of 1,000. And this number will in fact converge to a single number. And it is not the only way that we could converge to this number. Here is another expression which does so. All this one does so far faster. Here's how I might type this into the calculator. The first thing I would do is I would write the whole numbers into a list and store it. Then I would encode the pattern replacing this n over here with list 1, which will do it for every single value in list 1. Let's store that as list 2. Then we can go look at these outputs, but we can watch first the 2 and the 7 stabilize, and then the 1, and then the 8, and so on and so forth as we go down the list, the numbers becoming less and less various. In fact, the last two seem to match, at least to all the decimals displayed. Here's that number out to 5 decimal places. It is a known constant called Euler's number, named after Leonhard Euler, the mathematician who discovered it. Now, we can use this just the same as we would any positive base, because a positive base raised to some power, if equal to the same base raised to another power, means that the two powers must be equal. This is true because exponentiation is a one-to-one function. So this is true in the case of constants, but also in the case of functions, like 3x plus 7. And so to solve something that looks like this, we would simply set the two exponents to equal to each other, 3x plus 7 equal to 28. Solving, we get x equals 7. Question number 12 is a similar kind of evaluation type question. We are given a function, 7 times e to the x, and they want to know certain outputs for given inputs. Another way that we can use the calculator to do this is pressing y equals. We want to put this in as a function, 7 times e to the power of x. E to the x is listed here, and our x variable is here. Now we can go second graph to bring us to the table, and simply scrolling up or down, read off the values in question, at least out to some number of decimal places as we would like. Observing things for 3, -1, 0, 1, and 3, we get the following values. If more decimal places are required, and they're not pictured here, if we scroll over and scroll down, we can see all the decimal places that we would like. Here I have a Desmos graph drawn up for e to the x, 2 to the x, and 3 to the x. E is a constant between 2 and 3, and as such, we can see that its graph looks very similar to the graphs of 2 to the x and 3 to the x. In fact, it just appears to sort of take place between them a little bit closer to the graph of 3 to the x than it is to 2 to the x. Essentially, it looks just like any positive-based exponent with base greater than 1. And so if we're asked to graph something that looks like e to the x minus 3 itself minus 1, we can do this using transformations. So minusing 3 just means moving it to the right by 3 units, and minusing 1 on the outside of a function just shifts the graph 1 unit down. Here I've given a graph of e to the x, and I've tried to depict that it goes through this point e here, 2.718 approximately, at the value of 1. If I want to translate this as was indicated, I could take these 2 points and move them over. This will only be an approximation, of course, because e is going to be a decimal number. In fact, no fraction corresponds to it. So we're going to need to, do a little bit of hand waving here, or perhaps a graph template for e to the x will be provided. The actual homework question concerning this on the internet is going to ask you to actually select a graph rather than try to draw something by plotting points. So you won't have to worry about plotting the point e at all. Just like any exponential, the domain goes from negative infinity to positive infinity. The range of the graph in question would normally, for the parent function, be 0 to positive infinity. This one is going to go down to -1 to positive infinity. And that also brings the equation of the horizontal asymptote from y equals 0 down to y equals -1. Question 14 wants us to solve this equation. As before, we're really just going to equate the two exponents when the bases are the same. This gives us the following polynomial equation, which we can solve by factoring. I've now skipped some duplicates from 14 down to 19. I leave it up to you to figure the other ones out. 19 gives us a graph and asks us to find the translations and reflections which produced it from the graph y equals 2x, the parent graph. We can see that it's been vertically reflected and that also some translation has gone on. I would suggest marking some points on the graph so we can examine how those points are translated. Notice here we go from 0, 1 to 1, 2, and then to 2, 4. If I take a look down here, I see again going over 1, now down 1, and then over 1, down 2. That's going to correspond to these 3 points here. So we want to figure out how to get from here in green to these points down here. Well, one is vertical reflection. That's going to put a negative out in front of my function. The other is a right translation by 4 to bring this point here. That's going to put a -4 inside of the function. Finally, we're going to want to downshift everything by 7, which puts a minus 7 subtraction by 7 on the outside of the function. Here they give us a particular model of the number of COVID cases in Kentucky in a certain week of 2020. Now, they told us this was week 18. Now, if this t is measured in weeks, and I believe we can infer from the phrasing of the formula that it is, then we should plug in 18 in for t. This will give us c of t. So what is c of 18? It's 3,000 times 1.195 raised to the 18. This is calculator work, and we can type it in this way, and order of operations will take care of the rest. Let's round to the nearest whole number, since we're talking about people, and we have 74087. Now, the number of cases on October the 4th, they tell us that's week 24. So we would do the same thing here. We would plug in 24 into our function and evaluate. Let's not waste a bunch of time. Let's just press second enter and call up our last line and change this to a 24. And we get 215750. Now, this is pure exponential growth, right? It's rare that we ever experience phenomena for very long that exhibit pure exponential growth, because things will start to limit that growth. If it's growth of a population, sometimes it runs out of resources. If it's growth of a virus, sometimes it runs out of hosts. So it says here, actually, the number of cases was not 215,000. It was only 72,000. What does that tell us? It tells us that the model does not govern this particular outcome. In other words, that this model, which predicted a growth rate, did not stay at 19.5%. Actually, what it did was it decreased over time to a lower growth rate. So this question then asks us to evaluate what is c of 0. All right, well, if I plugged in a 0 into this exponent, we'd get something to the 0th power, which is 1. So this would just give us 3,000. And I believe they mean, is this consistent with the first point that we plotted, in which case, yes, it is consistent. That, or I've accidentally skipped some kind of table when I copied this problem over. I don't know exactly which table they're referring to here. But I do know that according to this model, if I were to plug in a 0 for my t value here, this would go away, and we would just be left with 3,000 times 1, or 3,000. All right, that's going to do it for this particular video. Thank you very much for your patience, and have a great day. Good luck with your studies. I'll see you in the next one.